Welcome to a video on the limits of functions of two variables. Let's start by reviewing what we know about limits of functions in one variable. If we want to consider the limit of f of x as x approaches c, it's equal to L only if the limit from the left and right of c also equal L. So it was important that we had to consider the limit from both sides to determine if the limit exists. Now if we consider a limit of a function in two variables, as xy approaches ab, the limit of f of xy is equal to L if the limit from all paths approaching ab exists and are equal to L. So what this is saying is, if this is the point AB on the surface, in order for that limit to exist, it doesn't matter which direction we approach this point, the limit must always equal L. So we could approach from this direction here, we could approach from this direction here, and there's an infinite number of paths that we could consider to determine if that limit exists. So we're going to have to figure out how are we going to determine a limit if there's potentially an infinite number of paths to consider. Well, there is one shortcut in some cases. Remember, with functions of one variable, if the function was continuous around the value of c, we could determine the limit by performing direct substitution. Remember, we took this value of c and just plugged it into the function if that function was continuous around that value. Well, the same is true for functions of two variables. If the function is continuous, then the limit as xy approaches ab of f of xy is equal to f of ab if we know the surface is nice and smooth and continuous. So if you have some graphing software where you can graph in 3D, that can often be helpful. It's important to remember that if a function is not continuous at ab, this does not mean the limit does not exist. We will need to consider approaching ab from different paths. So let's talk about the paths for a moment. If xy is approaching the point ab, we could consider letting x equal a, y equals b. We may also consider the paths of y equals x, maybe even y equals negative x, y equals x squared, x equals y squared, and so on. And these may help us determine if the limit exists or not. Let's go and take a look at some examples. Here we have the limit as xy approaches 1, 1 of this function in two variables. Now over here we do have the graph of the surface. We can quickly see there is some discontinuity. Let's see if we can locate where the point 1, 1 would be. Remember, we'd move out 1 along the x-axis, out 1 around the y-axis, and then up to the surface. So it looks like this point would be somewhere over here on the surface. And you can see around the region of this point, the surface is nice and smooth and continuous. This is an indication that we can just go ahead and perform direct substitution to determine this limit. Let's go ahead and do that. Looks like we're going to have 4 plus 2, that's 6, divided by 2, which is equal to 3. This limit is equal to 3, which tells us that as we approach the point 1, 1, the z value is approaching 3, so the height of this surface here is approaching 3. Now since this surface does have discontinuity, let's take a look at where that occurs. If we take a look at our denominator, if x and y were opposites, the denominator would be 0 and we would have discontinuity. So if we considered the path where y was equal to negative x, so if we replace y with negative x, we'd have a 0 in the denominator. This function would be discontinuous. And what I want you to notice is if we rotate this surface to look down on the xy plane, you can see the break in the surface, and this break occurs along the line y equals negative x. So what this tells us is if we considered the limit as xy approach, let's say 1, negative 1, or 2, negative 2, the limit would not exist. Not necessarily because of the discontinuity, but because we can see graphically if we approach those points along the line y equals negative x from different paths, the limits would be different. Here we have the limit as xy approaches 0, 0 of the given function. I've graphed the surface over here in 3D. Let's see if we can locate the point 0, 0. Well, when x is 0 and y is 0, we'd be at the origin, and then from there we'd go up to the surface. It's kind of unclear where that point would be. I don't know if it's up here or down here. Let's just kind of put a point somewhere here in the middle. We're approaching that point on the surface. And just from the graph of this surface, it is behaving a little bit strange right around the origin. One of the things we notice on this one is if we try to do direct substitution, notice we're going to have 0 over 0, which is an indeterminate form. And since we can't perform direct substitution, we're going to go ahead and approach this from two different paths and see what we discover. Let's consider the path where y is equal to x. Well, if y is equal to x, we can rewrite this limit as the limit as x comma x approaches 0, 0. Again, since y is equal to x, we can replace y with x. So if we replace y with x, this would become x times x, or x squared, all over x squared, plus, and then y squared would become x squared with the substitution. So this becomes the limit. This becomes x squared over 2x squared. We have a leading coefficient here of 1. And the reason I mention that is this simplifies. And notice now the simplified function is not even affected by x. So this limit along the path of y equals x is equal to positive 1/2. Now let's go ahead and consider the path y equals negative x. Let's rewrite the limit. We'll have the limit as x comma, now y is equal to negative x, so we'll have x negative x approaching 0, 0. Now let's perform the same substitution into the original function. We're replacing y with negative x, so we'll have x times negative x, it'll be negative x squared. Denominator is going to be x squared plus negative x squared, that's going to be positive x squared. We're going to have positive 2x squared. And this simplifies just like the last one. The x squared simplify out, and now this limit along the path y equals negative x is equal to negative 1/2. Since these two limits are not the same, we can conclude that this limit does not exist. So what we've done here is approached 0, 0 along this line here, y equals x, and then we approached along the line y equals negative x. And you can see the yellow limit was positive 1/2. The green limit was negative 1/2. They're not the same. Therefore, the limit doesn't exist. Let's take a look at a few more. Now, on this one, I just wanted to show it's the same function, but now we're approaching the point 4, 2. So even though we had a problem approaching 0, 0, well, the point 4, 2, we'd come out 4 along the x-axis, and then over 2 along the y-axis. We might be somewhere around here. And notice the surface is nice and continuous around this point. So we can go ahead and just perform direct substitution to determine the limit as xy approaches 4, 2. This would give us 4 times 2 all over 4 squared plus 2 squared. So just because there wasn't a limit approaching 0, 0 doesn't mean there won't be a limit approaching 4, 2. So here we're going to have 8 all over, this will be 16 plus 4, that's 20. This limit is going to be equal to 2/5. Here we have the limit as xy approaches 0, 0 of natural log x squared plus y squared. Here's the graph of the surface. And you see here I've also rotated it so we could get a nice view of the z-axis. So if I wanted to determine where the point would be as x and y approach 0, I would be approaching the origin here from all different directions. You can very easily see that as we approach the origin, this surface is going down very quickly. It's even more obvious on this graph here. So it's pretty easy to see from this surface that as x and y approach 0, z is approaching negative infinity, which means this limit does not exist. Another way to think of this would be to consider the graph of a function in two variables, which we should be familiar with. This graph looks something like this. And we know that as x approaches 0 from the right, this function value approaches negative infinity. So for the same reason, x squared plus y squared is going to approach 0 when x and y approach 0. Therefore, z is going to approach negative infinity. Let's take a look at this last one. Here we have the limit as xy approaches 2, 4. If you take a look at the graph of this surface, it might be kind of surprising. It looks like this is just a plane, and this definitely does not look like an equation for a plane. And if we try to perform direct substitution, our denominator is going to equal 0, so it's undefined at the point 2, 4. But this rational function can actually be simplified. The numerator is factorable because there's a common factor of y. So let's go ahead and factor the numerator. So we'll have y times y minus 2x all over y minus 2x. And notice that this rational function simplifies nicely, and when it simplifies, it eliminates that discontinuity. So now we just have the limit as xy approaches 2, 4 of y, and y is approaching 4, so this limit is equal to 4. So just like we saw with functions in terms of one variable, if the rational function can be simplified, it can often remove the discontinuity, making the limit much easier to determine. Okay, I hope you found these examples helpful. Thank you for watching.